Oh, but you.
All right, section 11.3, we're going to talk some more about angles in this section. We're going to define a lot of different types of angles at the get-go, and there's going to be several diagrams, but I think they're all in your notes this time. I got them all to cooperate with me, so that's good news. All right, the first thing we're going to talk about is vertical angles. Vertical angles are pairs of angles that appear across from each other whenever two lines intersect. And vertical angles are congruent. So taking a look at this particular diagram, this angle and this angle would be considered vertical angles. So we could talk about the pair of angles that's angle AEB and angle DEC. Or another pair of vertical angles would be what? What else could we write down as vertical angles? BEC and what, Catherine? AED. Okay, is everybody okay with the location of those? All right, so we can talk about the fact that these are congruent. Congruent means they have equal measure. And one of the simplest ways to argue that that would be true is if you take a look at, let me take a look at this diagram. What is the degree measure if you go across this entire angle AEC? 180. And I don't know what this measure is, but we could call it X, right? So that's 180, which means that this angle at the top is 180 minus X, just the piece at the top right here, right? My daughter was using my iPad yesterday, and she changed some of my settings, and I've been dealing with those settings being changed as I've found them all day. So this angle right here would be 180 minus X. And then you could do the same thing for this angle. This angle is also 180, right? The one that I just marked at the bottom, BED. But that means that this piece right here could be the 180 minus the same X that's on the right-hand side. So you get 180 minus whatever that measure is. I don't know what the number is, 30 degrees, 50 degrees, 72, whatever it is. You could subtract it off and you get the same measure for the top angle AEB and the bottom angle DEC. The vertical angles are congruent. Another type of description for angles would be, excuse me, complementary and supplementary. Complementary angles are two angles whose measures add up to 90 degrees. And the way we describe that is we say that one of these angles is the complement of the other. And we'll write down some complementary angles in a minute. Supplementary angles are two angles whose measures add up to 180 degrees. And we would say that one of these angles is the supplement of the other. Complement, supplement. It's about 90-degree angles, right angles, and 180-degree angles, which is a straight angle. Okay, so taking a look at the first diagram, there's a lot of descriptions that I could use. That is, there's a lot of pairs of complementary angles because there's a lot of angles in that diagram. But the kicker is that complementary angles are simply two of them. Okay, so we wouldn't say like these three angles are complementary. That's not appropriate. Complementary is always about the relationship between two angles. So I will give you one angle, and you guys tell me what the complement is. So if I do angle AOC, what would be the complement of angle AOC? COF, right. Okay, and we could create various other components just like that, right? Like there's nothing special about AOC. I could have done AOD, or I could have even written it as DOA. DOA is not a very good description, though. It actually is an acronym that means something not so nice. So, do you know what it is? Dead on arrival. Yeah, it's a happy thought. Okay, next diagram, the one at the bottom right. We're looking at supplementary angles. So, if I do in this diagram, angle AOB, what would the supplement to angle AOB be? BOD or DOB.
Will there ever be a time where a question I'd be asked, like, what's the supplement
It would, but in this diagram, there's not an angle that you could mark it that way. So it would have to be already present in the diagram to be described in that fashion. Yeah. Yep. Okay, any questions about those two? All right. This diagram is going to be present on all of the remaining, well, not all the remaining, but several of the remaining slides because it's useful. So other types of angles are formed when one line, called a transversal, intersects a pair of lines in a plane. So those two lines don't have to be parallel. They don't have to be, but often they are in what we're talking about. So in this diagram, it looks like which two lines are parallel? L and M. Do they have to be parallel? No. It would still be called a transversal even if those lines weren't parallel. Okay? So the transversal in this picture is T, and the pair of lines in this picture are L and M. Okay, so using this diagram, we can define relationships among all of those angles, and there's 8 angles described on this picture, right? They're labeled 1 through 8, in fact, which makes it easier than working with all the letters that we were working with in the other diagrams. So take a look at first what we mean by interior angles. Interior angles are angles that lie between the pair of lines. So which angles in this diagram are interior? We're going to list them all. 8. What's next? 3, 7, and 2. Those are my interior angles. Now, very specifically, we can talk about things called alternate interior angles. Now, alternate interior angles are pairs of interior angles that lie on opposite sides of the transversal, and they're not adjacent. So let me kind of go through. I'll give you an example of one and then show you how it meets the criterion. So a pair of alternate interior angles in this diagram would be angle 8 and angle 2. So here's angle 8 right here, and here's angle 2. One of them's on the left side and one of them's on the right side of the transversal, agreed? And they're not adjacent. Adjacent means right next to each other. So for example, 8 and 3 are on opposite sides of the transversal, correct? But they are adjacent. So that's not what we mean by alternate interior. We mean they're on alternate sides of the transversal, and they're not adjacent, okay, and they're in between the two lines. So this is alternate interior. There's another set of alternate interior angles. What else are they? 7 and 3. Okay, a couple more. The next one we're going to talk about are called exterior angles. Exterior angles are angles that lie outside the pair of lines. So where are your, or what are your exterior angles in this diagram? I think 4, 1, 5, and 6, or 1, 4, 5, and 6 were the ones that were mentioned. Okay? They're not between the two lines. They're either above both lines or below both lines. And those are the 4 that we have in this diagram. Much like we did alternate interior angles, we can do alternate exterior angles as well. So in this diagram, if 4 is one of my angles, 1 is on the opposite side of the transversal, but it's adjacent, so that's not correct. But on the other opposite side of the transversal, exterior, would be angle 6. Okay, is everybody with me? Those two are considered alternate exterior angles. So angle 4, that's what I marked, and angle 6. What are the other pair that we could write down? Yeah, angle 1 and angle 5. Those are alternate exterior angles as well. There is one more description of these different types of angles, and that's corresponding. Corresponding angles are angles that are in the same position where the transversal intersects one line and where it intersects the other line. So there are 4 pair of corresponding angles here. For example, here is angle 4. The one that corresponds to it down on line M is angle 7. It's in the same position, in this case top left. So angle 4 and angle 7. And there are others. So somebody tell me another one that you have. 3 and 6. I agree. 3 and 6. What's another one?
1 and 2.
1 and 2. And there's one more. 8 and 5. Yeah. Those are corresponding angles, angles that are in the same location or same position along the two different lines. So we already said that L and M don't have to be parallel, okay? We said that. But if the corresponding angles are congruent, then the alternate interior angles are congruent, and alternate exterior angles are congruent, and our lines are parallel. And not only is that true, but if any one of these 4 facts is true, you get them all 4 for free. Okay? So these are statements that are equivalent to one another. If I know that I have parallel lines, then I have all those congruent statements. If I know I have any one of those congruent statements, I know that I have parallel lines and the other congruent statements as well. These statements are equivalent to one another. Okay. We are going to do a short exercise. I'm going to describe this first one, and then we're going to use the next one. If you've got a piece of paper, you're going to need it in a minute. If not, you can borrow some from someone. I've got a notepad up here, too. Constructing parallel lines using a triangle. So go ahead and grab out, if you have it with you, a straight edge. So straight edge might be your ID card. If you have a ruler, grab your ruler out. It'll just make it easier to work with. But something that's got a straight edge to it. Okay? And because we're going to use it later anyway, you don't have to do this at this moment now, but because we're going to use it later anyway, if you have a sheet of paper, go ahead and take it out, and I want you to neatly tear apart a triangle. Okay? It does not need to be a right angle, although you might want it to be because it's simply easier to work with because you've got a corner of your paper already. But just create a triangle. Yep, out of the piece of paper. It needs to be somewhat small or you're going to not be able to draw it on your notes, okay? So somebody left their notepad up here, so I'm going to take piece of paper out. I meant to bring scissors, so my apologies about that. But you guys know, you guys are elementary ed and such majors, so you know how to create things like that. Yes, I know you do. You guys do bulletin boards and lots of fun stuff. Just a straight edge and tear it neatly. Not like me, because I did not just tear it neatly. It was awful. I'm going to try it again. Oh, look up here. Morgan's got some scissors, if you can convince her to share. All right, if you want some scissors, ask Morgan if she'll pass them around. I have napkins in my car.
I know. They were like,
why wouldn't you?
You should have these. I was like, I don't have any.
Yeah.
Yeah.
See, look at that. I've got a triangle. It's almost perfect. Okay, tear yourself a triangle. It does not have to be perfect, but the closer it is, the more convincing my next argument's going to be. So, okay, after you have this on your sheet of paper, I want you to draw one line anywhere, well, in that blank space, but you know what I'm saying. Draw me a line. And a point not on the line. Now what we're going to do is we're going to use this triangle that you've made to create a parallel line to the line we just drew through the point. Okay? It will probably help if, no, not necessarily, you don't need to, it's fine. I guess it would probably help if your diagram kind of mirrors mine a little bit, just so that you're not like, where did she put that ruler or whatever, okay? It would be helpful. Again, keep that straight edge out, something straight and flat against the edge, whether it's a sheet of paper or a ruler. Keep that out, okay? All right, so what we're going to do is you're going to take your triangle and you're going to line one of the sides of your triangle along the line you drew, okay? So it doesn't matter which side, but lie one of your sides of your triangle along the side over here. Don't do what I just did. I didn't create something that was a triangle at all. But that's not bad. Okay? So you've got a triangle that is resting on your picture. You don't need to draw it. You can if you want. You can trace it and draw it if you want. But your piece of paper that you've cut out that looks like a triangle or close to it, that's what I want to be on that sheet of paper. Okay? Here's the next thing you're going to do. Is you're going to take your ruler and put it along one of the sides. Hang on. I didn't draw that right. I want it to be underneath it. I could probably make it work otherwise, but it'll mirror my notes better if I put it underneath. How about like that? Let me do it that way. You can draw a triangle on there if you want. You're going to use this piece of paper in a minute anyway, so either use this one or don't use it for now, but you're going to need it later. So put your triangle underneath it. Okay, you're going to take your straight edge, your ruler, your whatever you have, and you're going to lie it along the, another side of the triangle. Okay, so it's going to extend potentially very far up. Okay, so you're going to put a ruler. That's not what I want. Okay, that red thing is supposed to be my ruler, okay? You guys pretend for a minute that's my ruler that's lying along the edge. And then what you're going to do is this. If you have the cutout and you're using it, this works really well. But the idea is that you take your triangle and you simply slide it up the ruler. So you're sliding the triangle up the ruler until it hits that line. So eventually, as you're sliding your triangle up your ruler, you eventually get a picture of your triangle. Hang on. If your lines are nicer than mine, they might be even friendlier to look at. Where it actually hits the corner, or maybe it hits some point in between. It hits the side of the triangle, if the triangle's big enough anyway. Hang on. I'm just shift it over here just so that I can see the picture better. Okay, you take the triangle and you're just shifting your triangle along the ruler. You're sliding it. Your triangle is sliding along the side of the ruler. Eventually it'll hit the point somewhere, the point in the top. So your triangle moves up, it just slides on up the ruler, and eventually it's going to hit that point. Okay? Yeah, eventually it hits the point. That point where it hits, right here, this line is parallel to the first line. Those lines are parallel. Because all you did is you took something and you created a congruent shape of it right up here. And the angles are the same because the shape's congruent, right? So this angle here at the bottom, like right here, is the same measure as this angle. This angle here in the top right is the same as this measure of the angle at the top right. So since you have congruent corresponding angles, according to our last theorem, your lines are parallel because your corresponding angles are congruent. So this line that I created up here along the side of the triangle is now parallel to this line that I originally started with at the bottom. And again, the reason is because corresponding angles are congruent. This angle is congruent to this angle, and so forth. You can mark any of them you'd like. The corresponding angles being congruent mean our lines are parallel. That's kind of fancy, and the reason it is because you didn't need to measure anything. There was nothing special about the triangle that you cut out to do that. I was kind of being a little bit particular on how far I wanted you to, make your point and your line away from each other, just because I wanted your triangle to be big enough to hit it. But the idea is still the same. Your point and your line, using a triangle of any shape, sliding it along the ruler will create a parallel line. Okay, you ready to do another activity with this? Okay, I know you know this statement's true. The sum of the interior angles of a triangle is 180 degrees, right? The three interior angles, 180 degrees. So take your triangle, and I want you to label the angles 1, 2, 3, or A, B, C. Just label them something, write it down. everybody have your triangle that's in pieces, or that is torn out, labeled. The next thing I want you to do is I want you to tear off the 3 angles. This is so cool. You're just going to love this. You're going to be so excited when you see what I'm going to do. I wish I had tape.
You tear all of them out.
Tear them all off. You should have 3 little pieces with an A, B, C, or a 1, 2, 3 all labeled on them. Okay, a bigger triangle might work a little bit better just because your pieces are small. Okay, now if you've cut them well, because you used Morgan scissors, then you've got really straight edges on 2 sides and a torn fuzzy edge on the third, right? Those really straight sides that you have, I want you to line them up next to one another. Okay? So straight sides beside each other. So if my lines are straight, or my edges were straight, it would look something like this. Straight edges beside each other.
Wait, to the piece that's not?
The piece that's a mess, like this is nothing. You just need the three corners.
Okay.
All you need are those 3 corners. Okay, just your 3 corners. Okay? And they should line up. I'm going to come around and do this in various places. Mine are not as straight as some of you guys'. Because this is not straight, but it's impermanent. Like that. Okay, you got it? Got it? Got it? That's perfect. You're good. There. Okay, yeah. All right, let me take a look here. That's perfect. Got it. The straight edge needs to be lining up right here. So line the straight edge up. Okay. Corners. Yep. 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 There it is. I see it. Okay. You're fine. Yes. Got it? Okay. That's okay. You got the right kind of idea here. Take a look over here. This is how they should be a little bit straighter. We're not very straight. Need it?
Oh, yeah.
Okay, so what do you see happen? No, not that. What do you see happen? There's a straight edge, correct? There should be a straight angle. And how many degrees are in a straight angle? 180. So your diagram ends up looking, we'll see how well I can draw it on here, something like this. And you've got this squiggly edges going on like here, and some of them are bigger than others and whatever you've got. But you've got this, and you've got them labeled A, B, C, or 1, 2, 3, or so forth. And the point is that those are the 3 angles that were in your triangle, correct? And when they're put side by side, they measure 180 degrees. So back in the original triangle, they would have also measured a sum of 180 degrees. Cool, right? Very simple to do, nothing really magical about it, and if you have scissors, it works better. Okay? So if that's what happens with a triangle, that is that the sum of the angles is 180 degrees, could you do the same exercise by creating a quadrilateral, a 4-sided shape? Could you tear off the 4 edges? Could you line them all up? I'm not going to do it with you, but could you? Sure, why not? You could do that. And when you do that, what you would actually find out is when you line all of them up with a quadrilateral, they would actually go all the way around. Because a quadrilateral's sum is actually 360 degrees. So it would actually go all the way around in a circle-ish sort of shape. That is, it would spin all the way around. It wouldn't actually have that straight edge that we just had on that straight angle. So what about the sums of the measures of the other angles of a polygon? Well, in a quadrilateral, you get 360 degrees. Now, I want to show it to you from the picture that's on here, though. If you take a quadrilateral, what you can do is you can actually break the quadrilateral up into 2 what? Triangles. And each of these triangles has 180 degrees in it, correct? So if you were to add 180 and 180, what are you going to get? 360, and that is the correct angle measurement for the angles sum inside of a quadrilateral. What would you do if you had a pentagon? How many triangles are there? 3. So what would you do to find the angle measure for 3 triangles? 180 times 3. This one up here was 180 times 2. What is 180 times 3? It is 540. Okay, so we just did 2 shapes. Do notice that the triangles need to come from the same vertex. So I used in my diagram down here this vertex to create my triangles. You can't just draw random triangles throughout this and create lots of them. That's not going to work very well, okay? So when you see the next shape for your hexagon, again, notice it's all breaking apart the triangle at the same corner, the same vertex. But how many triangles do you have on this one? 4. So we would do 180 times 4, which would give me what? 720 degrees. So take a look at the pattern. So we're talking in my number theory class right now about patterns. And one way to define a pattern is to notice what happens as a recursive relationship. That is, now I could do 7 sides, I'd add another 180. And then I do 8 sides and I'd add another 180. And I do 9 sides and add another 180. That's great. And if you want to know all the way up to a certain length, that works fine. But what if I asked you something about a 35-sided polygon? I don't want to add 180 up that many times, right? It's not very practical. So it's much more helpful to look at the pattern and see if there's a relationship that's not recursive. That is, that doesn't rely on the previous figure to know what the next figure would be. So take a look at the relationship between, all of these are 180 times something, right? So for a quadrilateral, it's times 2. For a pentagon, it's times 3. For a hexagon, it was times 4. You can, but that's a recursive relationship. That means you actually need to know what happened before it.
Number of sides.
By the number of sides, but subtracted by 2.
Yeah, I see several of you that were thinking that. Yes, Olivia?
Probably.
Not quite that way? Okay.
I was thinking maybe you could just count the little things.
Count the triangles inside? You could, but there's a nicer way to do it if the figure's bigger. Because I wouldn't want to draw a 35-sided figure probably, right? I don't think I could actually even do that. Once we get past about 8, I struggle. So if we had a large polygon, that is a polygon with many sides, a nicer way to recognize the relationship is how hexagon, 6-sided figure, is related to the number that I'm multiplying with, 4. And it's exactly how many fewer? 2. It's exactly 2 fewer. And take a look back. Does that work for pentagon? And does it work for quadrilateral? Yes, it does. So the number of sides, so we're going to take 180 degrees and we're going to multiply it by the number of sides minus 2. However many sides I have, it's 2 less than that. Number of sides minus 2. Now, there's a nicer way. I'm sorry, that is the number of triangles. I didn't mean the 180 there. My apologies, erase the 180 there. I was already writing down the next equation that you needed. Okay. Cut. All right, this isn't working. Let me try it one more time. Yes, Morgan, it is always going to be minus 2. I'm sorry.
180 or
This is why I tell you guys when you're doing your presentations not to use that eraser feature, and then I just went and did it. Number of sides minus 2. That's what's supposed to go in that blank. Number of triangles is the number of sides minus 2. Okay? So there's always 2 fewer triangles than there are sides of the shape you're working with. So if you had a 15-sided figure, how many triangles would you have? 13. Okay, just 2 less, 2 fewer. All right then, so if you're taking a look at this next one, some of the measures of the interior angles, you're going to take that number of sides minus 2, And you are going to multiply it by how many degrees are in a triangle. That is, you're multiplying the number of triangles times the degrees in a triangle. And how many degrees are there in the interior angles of triangle? 180. So this is sort of a visual description in words. If you're doing this where the number of sides is n, which it tells you right here, you can condense this to say that this is n minus 2 times 180. N minus 2 times 180. All right, we have a few examples. You guys ready? First one, very straightforward. We have a 37-sided polygon. Actually, that's a little worse than my 35 one that I just mentioned a minute ago, right? 37 sides. And we want to figure out what the sum of the interior angles is. How do we do that? Yep, I take 37 minus 2. You don't have to write that out. You could write 35 if you want to. And what are you going to multiply it by? 180. So if you grab your calculator for me, we're going to take 35 times 180. It's big. 6,300 degrees. And I definitely don't want to draw it to figure it out. I mean, by all means you can, but I'm not going to. Okay, here is a application of this. So we've got a figure. What is this shape? It's a pentagon. Okay, so the directions say a home plate in baseball has 3 right angles, they're marked there, and 2 other congruent angles. What is the measure of one of the 2 other congruent angles? How could I use the information that I know about this shape to figure out those 2 missing angles? Okay, so I first would need to know, or to remember, because we've actually looked at this one already, what's the sum of the angles, and by angles I do mean interior angles, in a pentagon? 540. So then, all of those angles that are inside there should add up to 540. What could you do next?
Subtract how many times 90 degrees come out.
Okay, and how many 90s are in there, Catherine?
3.
3. So if we take our 540 and we subtract off 90 degrees 3 times, or 90 degrees times 3. So that's 540 minus 270 is what that is. What am I left with? 270 degrees. Okay? Now what am I going to do with that 270? Right, and why?
Because there's 2 angles.
Right, there are 2 angles that are still remaining there that are not 90 degrees, and they are congruent. This would give me 135 degrees, which was what I was looking for.
Wait, yeah, one more time. Why did you divide by 2?
Because there's 2 angles here
Oh, okay.
that we haven't accounted for yet, basically. We accounted for the other 3 when we subtracted off the 90 times 3. Okay, we're going to ask the question from number 1 in reverse next. In a regular polygon, the measure of each interior angle is 162 degrees. How many sides does the polygon have? So that formula, if you will, that we created on the last couple slides ago, said if I take n minus 2 and I multiply it by 180, then this will give me the sum, right, of the angle. Now, we aren't told the sum on this one. We aren't told what the sum of the angles are. But we are told that each individual angle is 162 degrees. So if I have n angles, what is the sum of my interior angles? Well, we're going to have the n minus 2 over here. That's the number of triangles.
It would be 162.
Yes. Okay, I still have my 180 over here. I have 162 degrees per angle, and there are n angles. Each one's 162, so 162 times n would be the total sum of the angles in my triangle. And at this point, I have an algebra equation, right? So if we distribute this out, I have 180 degrees times n minus 360 degrees equals 162 degrees n. I need to get the n's on the same side, and I'm kind of a fan of making things positive, which means I would tend myself to move the 162 to the left. There's nothing special about that. If you move the 180 to the right, that's okay. You'll just have a negative number. So if I have this, I now have a 0 on the right. What's 180 minus 162? 18 degrees, n, minus 360. Then I need to move the constant to the right.
Where did you get the 360 from?
180 times 2,
Okay.
right here. Oh, that was supposed to be a highlighter. That didn't work at all. This piece, there we go.
Okay. Just to make sure I wasn't
So now I have 18 degrees n equals 360. And what would be my last step then? To divide. So 360 divided by 18, 20. This is a 20-sided figure. Okay, 2 more slides. I'm going to do it really quickly, and then we will save the other 2 things I was going to do for next time, okay? They're looking at your notebooks and checking out that one problem. Exterior angles. The exterior angles in this diagram are the blue ones. So the sum of the measures of the exterior angles of a convex polygon with n sides is 360 degrees. Doesn't matter if it's a hexagon, a decagon, a quadrilateral, or a triangle. Always 360 degrees. So this is in this picture, it's the beta 1 through beta 5. Beta 1, 2, 3, 4, and 5 in this picture. Those are all added together, going to be 360 degrees. Last question, and it's similar to one that's in your homework. Our goal is to figure out what the angle is for x in this diagram. And there's definitely more than one way to do this. But the cleanest way to do this is to use, at least in my opinion, is to use a pentagon. So if I were to drop a line down here, I would have a pentagon, right? Not only would I have a pentagon, but I've created it in such a way, just for convenience, that these are right angles. Yes? So how in the world could I figure out what the angle x would have to be? Yeah, it's much like the problem before. It's not nice and symmetric, but I have 540 degrees. And I can subtract off the pieces that I'm given. I was given 135 and 140. And then I put in the two 90-degree angles, and I'm able to do that because it told me the lines are parallel, by the way. That's an important piece of information. So if I take off 90 for each of my angles that I inserted to create the pentagon, what is the angle x going to be? 85 degrees. It's that easy. It looks so much more complicated. You can create triangles and things out of this and find the same thing, but the pentagon's a whole lot easier to work with. Okay?